Welcome to Hartman Math. Today we're going to talk about inverse functions. Prior to that, we do have a warm-up going over things we've discussed before. Go ahead and pause the video here and see if you can answer problems 1, 2, and 3. Now let's take a look at number 1. We're going to have 3 different sketches with some of the transformations based on this being our parent function. F of x plus 2. What kind of transformation is that? It's going to be a shift to the left by 2. So negative 5 comma 2 goes to negative 7 comma 2. All the points go left 2 from there. All right, what about part B? 3 times f of x minus 1. We've got a vertical stretch and a shift down 1. Stretch first, shift second. So if we kind of look at this first point, it's going to stretch to negative 5 comma 6 as we multiply the y-coordinate by 3, and then shifts down 1 down to 5. So we get negative 5 comma 5, 2 comma 5, negative 4 comma negative 10. So if we multiply this by 3 and then go down 1, and so on. The last one, 1/2 f of x minus 2. We've got a vertical shrink or compression and shift right 2. So like this point here, if we compress it by half, goes from 2 to 1. Half of 2 is 1. And then shift to the right from negative 5 to negative 3. All right, part 2, a little more practice on the difference formula there, the difference quotient. You should have gotten this one. It's not too bad, being it's only 2 terms there. You should have gotten 2x plus h. H cannot equal 0. And for our last one here, f is odd, g is even, h is neither. Today's lesson 1.9, inverse functions. You learned a lot about inverse functions in Math 3, the mechanics, being able to, the steps to go to find the inverse, and we will review those. We're also going to get more in depth into kind of domain and range issues again. So let's say we had f of x being x plus 4, the inverse function, we want to basically be able to undo it. So there's kind of the key phrase right there. Has the effect of undoing. Well, the undoing adding 4 would be subtracting 4. And this is the notation right there used for an inverse function, f, and it looks like an exponent of negative 1, but it's, as f is not a variable, it's just a name, we read that as f inverse of x. So just be aware that that's the notation there, would be x minus 4. And then by definition, if you do compose, as we talked about composition before, compose a function with its inverse, you always have to get x as a result. And if we reverse it, it's the same thing. You have to get x as a result. So what's happening with our domain of f is something happens with the function where we add 4 to it, and that takes us to the range of f. And that does have to match the domain of the inverse function. And then when we perform the inverse function by subtracting 4, it takes us right back to where we started. So for example, 2, we would add 4 and get 6. Subtract 4 and takes us right back to 2. So 2 comma 6 is in the is a point basically represented by the function f, whereas starting at 6 and getting back to 2 is representative of a point of the inverse function. So just definition here, 2 functions are inverses if you compose them and you get a result of x for every single x in the domain of g. Remember, g being the inner domain, something that we talked about last time. And conversely, if you reverse it, g of f of x has to be x for every x in the domain of f. So So under these conditions, the function g is the inverse of f, and there again is how we read it. That notation we read as f inverse. So f of f inverse of x will always be x, and vice versa. So example number 2, we're given 3 functions and we need to see if we can find out which of these 3 functions happen to be inverses. So we're going to attempt the composition to see if we can compose 2 functions and see if we get an output of x, and that would tell us that they are going to be inverses. So let's try f and g. So f of g of x, we're going to take the g of x and plug it into f. So the g of x, the x minus 8 over 5, replaces all the x's in the f function. So we're going to get 5. Replace this with this, plus 8. So let's see if we can simplify that. 5 divided by 5 is 1. 1 times x minus 8 is x minus 8, so essentially these cancel. We get x minus 8 plus 8, and we do get x. So we found out that f and g, those are inverses. Let's see if any others happen to be inverses. Okay. We could try some others if we want to go through it and see which other ones might be, but you're going to see as you go through that any of the others are not going to work. They're not going to be inverses. If we were looking at graphs of a function and its inverse, you would kind of notice that they are reflections of each other always in the diagonal line y equals x. So one flipped over that line y equals x would map onto the other, its inverse, and that's going to work always. So if we're looking at it in terms of the graph, you can say where is the inverse? All we have to do is reflect it. And the easy way to do that is go point by point, is just take the coordinates and just switch them. So if we've got over here, let's say this is 4, 2, and that's going to be 2, 4. All you have to do is reverse the coordinates. One-to-one functions. Okay? A one-to-one function, if we want to test a one-to-one function, we can use a horizontal line test to determine if a function is one-to-one. So that's the horizontal line test. And the definition of one-to-one is that when each value of the dependent variable corresponds to exactly one value of the independent variable. Function f has inverse only if it's one-to-one. So if a function is not one-to-one, then the entire function does not have an inverse. We might only be able to look at a small part of it. Example number 5, determine if the function is one-to-one. We've got a couple options here. We can look at it from a graphing perspective and see if it passes the horizontal line test, or we can look at it from an algebra perspective. If we do it from a graphing perspective, we've got our parent function, the squaring function, which is our standard parabola. Right here, if we pass a horizontal line across, it hits at 2 different places. So this function is not one-to-one. Another way of looking at that kind of algebraically, are there 2 different x values or input values that produce the same y value or output value? If that's the case, then it's not one-to-one. Not one-to-one, 2 different inputs produced the same output. All right, pause the video here, take a look at the checkpoint g of x equals x cubed, and see if you can determine if that function is a one-to-one function. If we look at the graph, which is another parent function, if we pass a horizontal line anywhere along, it will always hit at just one point. And that means that it is going to be a one-to-one function. So remember, for inverse purposes, this function would have an inverse, this function would not have an inverse. So this is the process that you looked at in Math 3 that would be able to find how you would find in the inverse of a function. So first off, we have to see if it actually has an inverse. Once you've determined that it's one-to-one and does have an inverse, we're going to take it from function notation, f of x, h of x, whatever, and write it as y equals. Switch the x and the y, and solve for y. Once we've got it solved for y, then we'll go back to function notation, but you have just found the inverse. So we're going to write it now as f inverse of x, or h inverse of x, whatever it was. And then lastly, if required, we can verify that the two functions are inverses by doing the composition both ways. All right, example 6. Find the inverse function of f of x equals 2x cubed minus 1. First off, is it one-to-one? Well, let's think about the function itself. It's the parent function x cubed, and then it's going to be stretched by a factor of 2, so we're just going to stretch it, and it still is going to pass the horizontal line test, and then if we shift it down 1, it's still going to pass the horizontal line test. So it is one-to-one. So in this case, we're going to kind of combine the first two steps. We're going to rewrite this as y equals and switch the x and the y. That gets us going on the switch and solve. So now our goal is to solve for the y. So we did these two steps in one. We rewrote this as y, and then we switched the x's and the y's. So to solve for the y, we should probably undo the minus 1. And then we can get rid of the 2. Divide by 2 on both sides. And how would we undo the exponent at this point? How do we undo cubing? We're going to cube root both sides. And when we do that, so we go from y equals, now let's rewrite that as f inverse of x equals the cube root of the x plus 1 over 2. So now our task, once we found the inverse, is to verify that this function and this function are inverses. And we're going to verify, which is a formal step. Must do that by the definition, which is using the composition. So here's our f of x, here's our f inverse of x. It doesn't really matter which one you go with first, but you have to use the titles. I typically like to do f of f inverse first. So we're going to start with the title. You have to have the title. Without that, not considered to be correct. So have the title, f of f inverse of x. And then we're going to take, here's our inner function, and we're going to plug it in there. So 2 times, replace the x with this, then cube it, then subtract 1. The setup part or the substitution part, very important, but also very important after that is to understand how does it simplify. And you have to go one step at a time. So what we're going to notice is at this point, the cubing and the cube root, they are inverses and they cancel each other out. So we have 2 times x plus 1 over 2 minus 1. And then we could do the 2 divided by 2 cancels out. And we get x plus 1 minus 1. Notice one step per step here. I'm not going to do multiple cancellations at a time. And lastly, these will cancel out, so we do get x. Now, I'll give you the secret, is me grading the work is I don't always necessarily look at this because I know that you know that you're going to finish with X. I'm going to look at the step before and see, did you have this part? All right, remember we have to show it both ways. We have to now reverse it, put F inverse on the outside, F on the inside. So again, have to have the title, F inverse of F of X. This time I'm plugging inner function, this, into here. So I'm going to replace that X with this. So I've got a big old cube root, I've got a fraction, this becomes that, plus 1 all over 2. Now this time, according to the order of operations, these don't cancel yet. Above and below fraction bars work there, so I'm going to say, even though they're parentheses, they don't really do anything here. The minus 1, the plus 1, they cancel out. I still have more work to do inside here. The 2 divided by 2, that cancels out. And now the cube root of x to the third becomes x. So one thing to check as you do this, look at the one that we did before and look at this one. If the step before looks nearly identical, it means you probably have made some sort of a simplification mistake. Example 6.5, let's explore the domain and range of the inverses. So same functions that we've been looking at. What about our domain and range, that kind of thing? So just as an example, not necessarily looking at the full domain and range, but what about points? What about x coordinates and y coordinates? For example, if we had the point 0 and plugged in a 0, you'd get -1. This point is on this graph. Well, when we go over to here, the -1, if we input the -1, we get 0. So -1 comma 0 is a point. Do we see the connection? If I plug in a 2, I'm going to get 15. So 2 comma 15. What if I plug in a 15 over here? I'm going to get 2. So think about it for a second. If I have this generic point A comma B that's on this graph, can you tell me the point that's going to be on this graph? Notice the relationship that we talked about earlier, reversing the coordinates, it would have to be B comma A. Example 7, find an inverse function algebraically. Find the inverse of f of x. If we thought about it for a moment, would this be 1 to 1? That's an important thing to think about. It is the parent graph that's just a square root function, starts at a point, goes to the right. We've got some horizontal compression, and that's not going to change anything, and a little bit of a horizontal shift. So still going to pass the horizontal line test. So it is 1 to 1, so we can find the inverse. Let's go about doing that. So let's say y equals, and then let's switch the y to an x and the x to a y. And if you go through that process, you're going to get x squared plus 3 over 2. Again, that's stuff that you worked on in Math 2, and we should be able to kind of get there and accomplish. But let's look at the domain and the range of each of these things. Like for example, the domain over here. Well, one thing that we do know is that we're only allowed to take the square root of things that are non-negative, so positive and 0. So we know that 2x minus 3 has to be greater than or equal to 0. And if we solve that for x, we're going to get x has to be greater than or equal to 3 over 2. So that's our domain. Let's think about the range. Okay? Let's think about the graph. It started at 0 and went up. We compressed it horizontally, so it still starts at 0 and goes up. We shifted to the right, still starts at 0 and goes up. So it really did not affect the range on the transformations there. So we're still going to get outputs of zeros and positives. Now let's take a look over here. What's the domain? Well, the domain in general is this function. If we were just to look at that, it's a parabola. It's been shifted. But that's just a polynomial function, so it should be all real numbers. But here's the thing. In order for us to talk about the domain of the inverse, it has to match the range of the original, because otherwise it's not going to pass the appropriate test. It's not going to have that thing where we reflect the graph across that diagonal line y equals x, and it matches up. So we actually have to cut down the domain on this one to match the range of the original function. It could not be all real numbers because it has to match here. And this is going to have to match that. And it would is in any case as well, but it has to match there. So that here are the graphs where that graph is here. And if we looked at the whole thing over here, we would have had a full parabola. But then the graphs don't match up as being reflections of each other, which is why we had to do this and say only look at this side, get rid of the part that's left of 0. So make sure for your function and your inverse, the domain and range match interchangeably. The domain of the function matches the range of the inverse. The domain of the inverse matches the range of the original. Example 7.5, find an inverse if possible. Kind of go through that again. Another square root function. So we should be pretty comfortable that this is going to be 1-to-1, and therefore we can find the inverse. So yep, it's 1-to-1. That's what the graph looks like. Let's go ahead and find the inverse. Y equals the square root of x plus 1. Switch the x and the y. Solve for y. Square both sides. And we would get something like this. If you wanted to do the squaring, you definitely could. We have the same thing. So now the question is, what is the domain of the inverse? If we were just looking at this as a function unto itself, okay, I can take any number, subtract 1, and square it. But again, remember, our domain here has to match the range back here. What's our range here? How low does it go? How high does it go? It goes from 1 to infinity. So we have to have that be the same thing here. For the inverse, its domain has to be from 1 to infinity. So you have to include that when you're doing the inverse, because it has to match the range of the other. That's it for today. See you next time.